Hi, my name is Christopher Meyer, and this is my lab for Circuits and Capacitors Physics 2. The goal of this lab was to predict the behavior of the circuits containing resistors in series and parallel and use multimeters to measure the actual values of conventional current and potential differences in the circuit, while also examining the behavior of ohmic resistors and capacitors. The results I received for the time constant was 5.1 seconds, the current was 0.02 amps, and the discharge times for 10 ohm bulb and 20 ohm bulb were 12.73 seconds, 12.69 seconds, 19.87 seconds, and 19.93 seconds, respectively. Key ideas we use in this lab are Kirchhoff's loop rule, the node rule, Ohm's law, as well as finding an equivalent resistor in parallel and in series. To begin, we started with series circuits, which followed with two ammeters. We set it up with two batteries, each of 1.5 volts, two resistors of 47 ohms and 100 ohms, and then we would find the reading in the ammeters and predict it initially, which gave us to be 0.0204 amps, whereas the computer model showed us a 0.02 amps value, which I believe is rounded. Now, what if we flip the ammeter? We would just notice that the current calculated would become negative. Next, we would attach a voltmeter to the series circuit. This voltmeter would act as an infinite resistance and halt the flow of electrons, so the voltmeter reading would only give us 3 volts because of the batteries, while the ammeter reading would give us 0 amps because the circuit is now completed by an infinite resistor and therefore has no current. Next, we would measure the voltage and the current at each different potential difference. So starting off to the graph on the right, the image on the right, you can see it goes from A to B, B to C, C to D, D to E, etc., etc. You'd find the current is all the same throughout every location because the series is in series. The circuit is in series, which is 0.02 amps. And once we sum up the voltages, we can find that the potential difference would come out to be 0, which should occur noted by Kirchhoff's loop rule. Here's a potential versus position graph where we can see the potential plotted against the different positions in the series circuit. Next, we would make changes to the circuit. First change was putting a voltmeter in parallel. This would create an additional path of infinite resistance, so the current wouldn't change because the current would just not flow through that path and rather just go through the 100 ohm resistor. However, if we made an ammeter in parallel, it would create an additional path which has 0 resistance, so the current would then flow through it instead of the 100 ohm resistor, decreasing the resistance equivalent of the entire circuit, and therefore making the current now 0.06 amps. Finally, next we would calculate the resistance using both the change in voltage as well as the current we have found. We would find that the resistance on the 47 ohm resistor was actually 47, for the 100 ohm resistor was actually 100, and for the wire and ammeter we would find both the resistance to be 0. Next, we would set up an RC circuit using a 9-volt battery, 200 millifarad capacitor, 10 ohm bulb, and 20 ohm bulb. We noticed that as the capacitor was charging, we would see the bulb light up fast, but as time passes by, it would taper off, as well as the current flowing quickly in while it was charging to light the bulb and then eventually slow. While it was discharging, we would notice the same trend where the bulb would light up fast and bright, but begin to taper off as the capacitor discharges, and the current would also flow quickly but in the opposite direction and slow down until the charge became 0. Now, for charging a 10 ohm bulb and a 20 ohm bulb, we found the times. To charge for the 10 ohm bulb, it was 12.73 seconds, and the discharge time 12.69. 20 ohm bulb, the charge time was 9.87 seconds, and the discharge 19.93. Next, we would try to find the time constant, RC. To do this, we would create a plot of the natural log of the voltage over the V0, which is the initial voltage, versus time. Using 20 data points from the circuit running on the computational model, we would find that the RC value was 5.10 seconds, and this would agree with the RC value of the circuit, which we can find to be 6. Finally, the reflection questions. The first question asks, what if we use an actual ammeter instead of an ideal simulated ammeter, and what would be different, and how would it affect the circuit? Well, in real life, an ammeter actually has a small bit of resistance, so the result would cause the overall current reading to be actually a little smaller than the ideal value predicted. The next question asks, now what if we did this lab in real life and used a battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict it to reach full charge, whereas compared to real life? In the ideal model, the capacitor would charge almost immediately. However, in real life, it would take a little bit more time to charge the capacitor because of these wires. and every component in the circuit in real life has actual resistance and would therefore slow the current. Thank you, and that is all.